Hello everyone, I'm Murtaza Safari, and today I want to talk about how you can calculate the velocity distribution within a microchannel in laminar flow regime. So to do that, we provide an example for you in which we have a simple microchannel with rectangular cross section. You can see the dimension here. The width of the microchannel is 300 micron, the height is 100 micron, and the length of this microchannel is 1000 micron. And we have water as our inlet with volume flow rate of 0.3 per minute, and the outlet, in outlet we have water that goes to atmosphere. So the objective of this example is plotting the velocity distribution in the middle of this microchannel. Of course, you can plot velocity distribution in different part of this microchannel. It doesn't really matter. So the objective is really extracting the velocity distribution inside the microchannel. So to do that, we switch to Comsol to explain how you can calculate the velocity distribution using Comsol Multiphysics. So when you start Comsol, you will see this kind of environment, and we choose Model Wizard here. So here you should actually select the space dimension in which you want to do your simulation. And as you saw in our presentation, we had a 3D microchannel, so we use 3D space. And the next step is selecting the physics. So the most correct way to determine whether the flow regime is laminar or not is actually calculating the Reynolds number. So I did that, and you don't have to be worried about that. The Reynolds number is less than 2,300, so that's okay. And the regime, the flow regime, is laminar flow. So to find the laminar flow regime in Comsol, you come up here in fluid flow, and in single phase flow you choose laminar flow. By double clicking on this, you have this physics in this section here, which is entitled Added Physics Interface. So you can move on to the study. So the study here, selecting the study is it means do you want to solve your equation in time-dependent manner or in a stationary manner? So we want to solve our equation in a stationary manner, so I choose a stationary, and I hit on done. So this is the environment that you will see when you do all of these things that I told you. So as you can see here, we have four main parts in this Comsol simulation environments. We have upper part by which you can actually do everything. You can build the geometry. You can select the material. You can select the physics. Meshing, study. Doing post processing. You can pretty much do everything. But the most part that we working on during the simulation is model builder, setting, and graphics. So in model builder you see different option here. Let's just do this simulation step by step. So the first step, which is not necessary but I highly recommend to do that, is defining the parameters for your example. And for this example I want to define 4 parameters: one for width, one for height, and one for length, and one for the volume flow rate. So here I write the name of this parameter. I type width. You can simply just type W. It doesn't matter really, as long as that W means width. That's totally okay. So the width is 300 micron, and you can add a description. Let me just. All right. You can add a description here. For instance, you can write this is the width of the microchannel. You don't have to again do that, but it's just for you. It's description for you. It really doesn't matter. It doesn't affect your simulation or your results. So the next parameter is h, which is height of the microchannel, and is 100 micron, and the other one is L, which is length of the microchannel, and it's 1000 micron. And the last part is Q. The last parameter is Q, and it's 0.3 milliliter per minute. And you don't have to include these units here, but again I recommend you to do that. It helps you it helps you to avoid mistakes during simulation. So the next step is defining the geometry. So in order to define the geometry or build the geometry in Comsol, you can use different softwares, AutoCAD, CATIA, SolidWorks, or other softwares. But for actually simple geometries, Comsol will help you to actually build a simple geometry by using very simple commands that you can use in Comsol. So if you right click on the geometry, you will see this menu, and you can see, for instance, you can build a block, cylinder, sphere, or by combination of these objects, you can build complex geometries as well. So here I have a rectangle, a microchannel with rectangular cross section. So I choose block, and the width is I use the parameter that I defined before. So the depth is L, and the height is H. So this is the size of this rectangle, and if you hit on this button, you can see your rectangle here, and you can change the location of this rectangle in this space. For instance, the position of corner for this rectangle is located in 0, 0, 0. You can choose center, which means this now the center of this rectangle will be located in 0, 0, 0. And if I hit on button build selected, you see that it moves to this location. So we don't have to do that, but sometimes in order to build a complex geometries, maybe you have to do that. All right, that's pretty much that you have to do in geometry. The next step is defining material. So to do that, you right click on material, and you select add material from library. And in Comsol, you see different libraries. In all of these libraries, you can find many materials, but finding your material from by looking for it in these libraries, it's really hard. The best things that you can do is just typing water here, because the material for us, the fluid, was water. So I choose H2O in liquid phase here, and I double click on it, and I will have it in the material section. So as you can see, you should define a domain for this material. Here we have one domain, so the Comsol by default just select this one domain for us, and the Comsol now recognize this rectangle as a water, as a H2O. So that's it about material. And the next step is setting up the boundary condition and taking care of the physics of laminar flow. So when you select laminar flow, you will see we have the domain selection here. Again, by default, Comsol select this domain because we only have one domain. So here in the equation part, you will see two equations, which is, I'm sure, that's familiar for you. This is the conservation of momentum, and this is the conservation of mass. And of course, by assuming the fluid is incompressible, because the density is constant in these equations. So if you want to simulate a compressible flow, you can have that, but here, as you know, the water is incompressible, so you don't have to choose compressible flow. And also you can make some assumption here. For instance, you can include the gravity, you can enable the prose media domain, and I don't want to talk about these things because I'm going to show you how you can work with these things in future. So for now, let's just think it's a simple rectangle, and water is flowing through it. And also we have a reference pressure and reference temperature, which is by default Comsol choose 1 atmosphere for reference pressure and 293, almost 293 for reference temperature. And you don't have to change anything in this part. For turbulency, we don't have any turbulency because we have laminar flow. And for discretization, the dependence parameter, you don't have to change anything. I'm gonna show you that when you should change these things, but you don't have to change discretization for now. So here in dependent variable, you will see all the dependent variable: velocity component, U, V, W, and P, which is pressure. So in fluid property, again, you have domain selection. Again, Comsol choose this domain by default. and you will see the fluid properties here. And you can, instead of reading density and viscosity from material, you can actually choose user defined here, and you can directly write the density of the fluid for which you want to do the simulation. But since we define the material, we don't have to do that. So defining the material is not necessary in this case, but it's really simple. It's best way to do that, because it's really simple to do that, because Comsol will take care of this density and dynamic viscosity by itself. So for initial value, you don't have to change anything. For initial value, you consider fluid and pressure to be 0, and for walls, we will consider no slip condition as a boundary condition. And you can see all of these walls, all of these faces are considered to be walls, and no slip condition apply for all of them. So that we have inlet and outlet, and it's not, no slip condition is not true for inlet and outlet. And I mean, we don't want to do that. We don't want that boundary condition for our inlet and outlet. So you can't change anything. You can't change any of these unless you define an inlet and outlet. By right-clicking on the physics, you will see this menu, and in this menu you will choose the inlet and outlet. So for inlet, I choose this face, and for outlet, I choose this face. So for inlet, we can define inlet using velocity, using pressure, using mass flow, using fully developed flow, and we consider the flow is flow fully developed in this example. When you choose fully developed flow, you can include the average velocity or flow rate or average pressure. I choose flow rate, and here I use Q, which is a parameter, and I define it for Comsol, so Comsol know that the Q is the flow rate. So that's pretty much about inlet. So let's move on to outlet. For outlet, as you saw in the presentation, we assume that water went to atmosphere. So in atmosphere, the gauge pressure is 0, because the absolute pressure is 1 atmosphere. So the gauge pressure is 0. So you don't have to actually write a number here. You don't have to change anything. Simply just choosing this face as outlet, that's enough for outlet. So let's just move on to the wall. And it's really interesting, because you see that these two faces, which is now for Comsol is inlet and outlet, are no longer a part of wall. So as you can see here in domain selection, these two boundary 2 and 5 is not a wall anymore. So that's about the physics. You don't have to change anything anymore. And let's move on to mesh. So in order to solve the equation using numerical methods, you have to mesh your geometry. You can mesh your geometry by yourself, but you can use the Comsol default mesh. And I want to do that in this section, and I will tell you how you can build your mesh in Comsol by yourself. And as you can see, we use physics control mesh, and we have an option here called element size. You can choose normal, coarse, fine, finer. When you go up, the element size will be smaller, and these option down here include very large elements. So it's really dependent on what you are looking for. If you want to calculate the fluid velocity with really high accuracy, so I recommend to use this option up here. Actually, in order to determine whether you calculate the fluid velocity right or wrong, you have to validate your simulation. But we don't want to talk about these things. And I choose coarser mesh, and let's just hit on build all, and you see that this is the mesh that Comsol use do the simulation here. And it's a really good mesh. I'm satisfied with it. So that's about mesh. Let's just run the simulation. You don't have to change anything in study tab here. Just hit on compute, and based on your computer characterization, in terms of CPU and RAM, it may take a while to run this simulation. So I just pause the video, and I will come back to you when I gain the results. So the Comsol finish running the simulation. So by default, Comsol plots some parameters for you, And for instance, as you can see, Comsol plot the velocity distribution in this cut plane for you, and you can see the colors determine the velocity magnitude in meters per second. So what I want to do, and you can also see the pressure distribution here. The pressure is really high, and here the pressure is almost zero, as you can see. And that's, all we expect because we choose the pressure to be zero here in our boundary conditions. So what I want to do is that I want to plot the velocity distribution in a plane, in just one single plane, in the middle of this microchannel. So in dataset, by right-clicking on dataset, you choose cut plane, and in cut plane, you choose the can plot a plane, and by inserting the location of that plane. So what I want to do is that I choose the plane in XZ direction, and in Y coordinates I insert 0. And if I plot, as you can see, we have a plane in the middle of the microchannel. Next, I right click on results and choose 2D plot group, because I want to plot a velocity distribution in a plane. So I choose cut plane 1, and by right clicking on 2D plot group I choose surface, and here I include the expression. Expression means the parameter that you want to plot. So if you want to, for instance, plot the velocity magnitude, by hitting on this button, you will see all of the parameters that you can plot. You can find the velocity magnitude in laminar flow, in velocity and pressure, here velocity magnitude. And if you hit on plot, you can see the velocity distribution in the middle of the microchannel. And if you want to see this in the microchannel, you can just add a 3D plot group, and by using a surface and choosing cut plane as its data set, cut plane 1 and its data set, here you have your velocity distribution in the middle of the microchannel. So let's say we want to plot a velocity distribution in a line in the middle of the microchannel. So I actually draw a cut line instead of cut plane. So I choose cut line 3D, and I want to plot this cut line in this cut plane, because this cut plane is already located in the middle of the microchannel. So what I want to do, oh, I'm sorry, I made a mistake. Instead of cut line 3D, I should choose cut line 2D, because I want to plot this cut line in this plane, so it's 2D environment. So I choose cut plane as my data set, cut plane 1 as my data set. So if you plot it, you can see this line, and we don't want this line. We want a line from here to here. So we want to have a constant x, and in y direction we include the width, half of width actually, and minus half of width. And if you hit on plot, you can see this cut line. And to plot a velocity distribution on this line, by right clicking on the results, you choose 1D plot group, and here you right click on 1D plot group and choose line graph, and in line graph data set you choose cut line 2D2, and here Comsol already by default include the velocity distribution for us in expression. So by just plotting, you can see this is the velocity distribution that Comsol calculate for us. And I have a fun experiment for you. You can, as you can see, this is not the kind of graph that we are looking for. I'm pretty sure that you saw the velocity distribution in a rectangular microchannel in your textbook, and it's not like this. It's really smooth. So to achieve a smooth graph for velocity distribution, which is correct, which is more accurate actually, you can change the mesh to be finer. So let's just choose finer element size and see what's happened. So I hit on study. So here it may take a while because we choose finer mesh and we actually use smaller element size. That means we have higher number of elements. So I just pause the video and I will come back to you when run is finished. So the run is finished, and let's check the velocity distribution in the cut line that's previously we plot. It may take a while to plot that. Yeah. As you can see, this plot is much more better compared to the previous results. So as you can see, by increasing the number of elements or by decreasing the size of elements, you can get more accurate results. And also, that doesn't mean you have to always just use the smallest element size, you should do mesh dependency analysis to make sure in what mesh, in what element size, the results do not change significantly compared to larger mesh. So as you can see, these are the results in different mesh. Here in the left panel, we have velocity distribution in the middle of the microchannel when we use coarser mesh, and when we reduce the size of the elements, we got this really smooth curve, which I think will agree with analytical solutions, analytical results, and still you have to compare these results to analytical solutions and make sure you didn't make any mistakes during the simulation. Of course, these two graphs doesn't mean that fine mesh is the optimal mesh that we should use in our simulation. In all of your simulation cases, before jumping into just extracting your results, you have to do mesh dependency analysis. And if you wonder what is mesh dependency analysis, I will explain you this concept in the future in our next episodes. Thank you for watching this session, and I invite you to watch our next sessions as well. And I hope this tutorial helps you to solve your problems while simulating using Comsol Multiphysics.